Hi, my name's Carmelo.
My name is Ethan.
My name is Lucas.
Mine is Marcos.
And we're Team Spaghetti Code. We created an app for NASA's 2024 App Development Challenge.
We use C# and Python with Unity to visualize the data provided to us from NASA.
Through passionate programming, we built an app that we are confident exceeds the expectations given to us.
In this video, we will describe the app in its entirety, the research we conducted, and the unique characteristics that we added to the app.
We will describe key obstacles that we faced,
key skills we acquired,
and the key mentor we learned from.
We will finish up with talking about the outreach events that we performed to better the STEM environment in our school, as well as future events that we have planned. We gathered the criteria for a landing site from NASA and other research papers. We chose the Leibnitz Beta Plateau for its high concentration in ice water, while still having roughly 65% of its slope under 15 degrees, and having an orientation towards Earth. For the destination site, we wanted to ensure that it had multiple permanent dark areas to explore of less than 20 degree slope to make it less hazardous for astronauts. We chose the destination that has 3 craters with slopes less than 20 degrees and still greater than 15 degrees. Lastly, the area of interest along the path is a small permanent dark spot marked in purple that would act as a training area before exploring the crater in green. It is also important to note that certain spots on our landing site are shielded from the Earth by the Moon, which blocks radio communication. If quantum communication was utilized by the astronauts on the Moon, they would be able to bypass radio blockage by using the quantum properties of entanglement and superposition, allowing astronauts to communicate from theoretically infinite distances, regardless of the medium between the astronauts and NASA.
In order to create as immersive and enjoyable an experience as possible, we decided to model our own rover, lunar lander, and lunar base. We used Blender extensively throughout this process. Our models, particularly the rover, were inspired by real designs being used in the Artemis mission. To make our rover drive, we first added a rigid body component to make our rover affected by gravity. Then we used a simple car controller and wheels to make it move.
We built the landing site in Unity by converting the height data given to us to a 16-bit image and imported it into Unity's terrain tools. We used a lunar surface image with a normal map to add an extra 3D texture to the terrain. Our app visualizes all the data provided to us about the Leibnitz Beta Plateau through color maps and on-screen data points. The color maps we created and displayed directly on our terrain include the height, slope, azimuth angle, and elevation angle. These color maps and the gradient were made with our own functions in Python. In Python, we started by creating 2D arrays for the data we needed to visualize. The height and slope were easy as the data came directly out of the CSV files given, but the elevation and azimuth angles had the extra step of needing to pass the data from select CSV files through mathematical formulas to get the correct value. We then could pass these individual 2D arrays into our map-making function. This function found the maximum value and the minimum value of the array and then scaled all other values according to this one. The scaled values were converted to an RGB value, which were all saved into an image. After getting the image, we created a texture for it in Unity and overlaid it on the terrain. For a pathfinding algorithm, we wanted to take on the challenge of creating our own as opposed to using one of Unity's built-in versions. We did this to learn the intricacies of graph algorithms and pathfinding, and we were successful as we created a pathfinding algorithm that allowed for optimizations including shortest path and least height climbed, which kept in mind the slope requirements. Our pathfinding algorithm was based off the A* search algorithm. A* is a best search first algorithm. This means given a weighted graph, it finds the most optimized path from the start to finish by repeatedly choosing the minimum cost node. This minimum cost node is the node which costs the least amount to travel to based off of the weighted graph. We applied the A* algorithm to our problem by creating the necessary weighted graphs. The weighted graphs were first put through the slope data to create a maze of which positions with too high slope cannot be traveled to. This allowed good modularity as one variable could change the path slope requirement to anything. Our shortest path weighted graph was based on every node's distance from the destination site. The nodes closer to the destination had smaller values, which led to the algorithm to continuously choose closer and closer nodes, of course avoiding spots where the slope is too large. Our least height climbed weighted graph was more complicated as different paths to nodes led to them having a different value. We solved this problem by calculating the node's cost while the algorithm was running instead of beforehand. By keeping track of the height climbed to get to a node and the height climbed needed to get to the next node, we were still able to apply the A-star algorithm. We created paths for the least height climbed, shortest path with 15-degree maximum slope requirement, and shortest path with 20-degree maximum slope requirement. We also calculated the length of each path by calculating how many nodes the algorithm traveled to. We then loaded this data onto our Unity scenes, displaying each path with a different color and length of the path. We also made an algorithm to place communication links from the landing to destination site path, which was optimized by getting maximum distance between each link. The algorithm first checked every spot along the path if it was in view of Earth, essentially checking if the elevation angle to the Earth was greater than the elevation angle to the horizon at the same azimuth angle, and this was through raycasts. These raycasts work by shooting a laser from a position on the path in the direction of the Earth and checking to see if it hit the terrain. After seeing which places could not hold a communication link, the algorithm determined which positions along the path resulted in the optimum distance between them. It did this by running a repeated binary search to check if a certain distance between communication links could be achieved. This loop ran until it finds the maximum distance between the communication links and then returns the positions along the path of the optimum communication links. The algorithm then automatically places the 3D modeled communication links on the correct position facing Earth.
The main challenges we encountered were the least height climbed optimization algorithm and general teamwork operations. We solved both issues by applying knowledge from our dual enrollment courses at West Virginia University, specifically the knowledge we gained in greedy algorithm programming and the V model in systems engineering.
For the first update of our app, we focused on polishing the app to create a final product experience. Menus were added to make the game UI more navigable. Toggles were created that can easily switch the data being shown, switching from colored surfaces to showing any combination of paths at a time. A mini-map has been added, and it shows the areas of interest on the lunar surface. More information on the data shown has also been added as a clickable UI element. We also updated the rover hitboxes to be more accurate to the model, although in a future update, we would love to make the wheels dynamically change their height throughout the runtime of the game.
We completed 2 outreach events, one for our elementary students and one for our middle school students. Both events included a detailed slideshow. The elementary event included an activity to teach kids about how bits are used in computers. The middle school event included a questionnaire about quantum activities, and we included a simple math solver program that allowed them to get hands-on programming experience. We gain interest in these events through social media outreach from our school.
We see a version of this app supporting future training activities by allowing astronauts to memorize exactly what route they will be taking on the moon, and through a virtual reality implication, even walk, research, and navigate the path themselves. Our best practices are contained in following the proper system engineering design process as outlined by NASA, allowing our programming work and teamwork to fall into place. The main development we would pursue with more time would be modifying the app's structure to work with virtual reality operating systems to bring about an unbeatable, immersive experience.